Good morning everyone. Last time we have discussed about the physical property of haloalkane and haloarene, and this time we are going to discuss about the chemical properties of haloalkane and haloarene. When you will discuss about the chemical property, the haloalkanes are the saturated system. Being saturated, they will undergo either substitution reaction or the elimination reaction. The addition reactions in the case of the saturated systems are not possible. And when you will see the nature of the halogens, they are electronegative. So a positive center will be developed on the carbon on which the halogens are directly attached. So that carbon will provide the nucleophilic substitution reactions condition. That means the condition for the nucleophilic substitution reaction. So here we are going to see the chemical property, and in that chemical property we are going to see the nucleophilic substitution reaction, which is well known as SN reaction, substitution nucleophilic. We are taking the simplest example. When haloalkane, I am taking methyl chloride, is treated with aqueous KOH, it forms CH3OH plus KCl. A substitution reaction, the Cl is substituted by the hydroxyl group. This is called substitution nucleophilic or the nucleophilic substitution reaction. We have to discuss about its mechanism, how the reaction proceeds, what is the mechanism for the reaction, what are the steps for the reaction. And when you will discuss about the reaction mechanism, there are two different mechanisms for the reaction. The first one is called the substitution nucleophilic bimolecular, and second one the unimolecular. So we are starting with the substitution nucleophilic bimolecular, which is well known as SN2 reaction. So we are going for the SN2 mechanism. What will be the condition for the SN2 mechanism? In the case of SN2 mechanism, the non-protic solvent will be used. So it is in any of the mechanism, the first step is always the generation of the attacking group, and here attacking group will be the hydroxyl group. So we are going to generate the hydroxyl group. Here this KOH will break in the form of the K plus and OH minus, because it is a strong electrolyte. So very strong polar condition is not needed for this compound. This have a big tendency to dissociate in the form of their ions. So here it is the cation and anion, means the nucleophile. This nucleophile will now approach on the haloalkane. This is the haloalkane CH3Cl. Then first, what type of the reaction, what type of the next step will be here? The first condition, the system will break in the form of the CH3 positive and Cl negative. That means the carbocation generation will take place. And the second condition, the hydroxyl group will approach on the system. Here the hydroxyl group will directly approach, because the solvent is not capable to break the CH3Cl in the form of their ions, because the solvent is non-protic solvent. So when the hydroxyl will approach, it will approach from back. बैक से क्यों? क्या ये शर्माता है आगे से आने में? श्योरली नहीं. When you will see the nature of the hydroxyl, that is negatively charged, and when you will see the nature of this species, the chlorine have a partial negative charge. So identical charge repulsion will act, and this is the reason why hydroxyl will approach from the back. And when this hydroxyl will approach, what happens? There will be a condition when one of the bond, that is the CCl bond, is about to break and hydroxyl bond is going to form. A highly unstable pentavalent intermediate, and finally this compound will break to form CH3OH along with Cl minus, and this Cl minus will again approach with the K plus to form the KCl. So here it will be K plus Cl minus giving KCl, and this is the overall reaction. Just note it down, then we will discuss about the next. When we will see the stability of this intermediate, that is the pentavalent intermediate, how much stable it is, whether it is stable or unstable, when we will discuss about its stability, we knew that the carbon have capacity to make the maximum of 4 covalent bond, that is the maximum covalency 4. So carbon is not going to form 5 bonds at any time, but this is a transition phase. You can say that this compound is turning in the form of the product, the reactant is turning in the form of the product. Then what will be the stability of this species? This species is this much unstable that we are not capable to recognize that whether this compound is going to form or not. But the product can be explained only on the basis of this mechanism. So we say that this intermediate is formed. So we are not capable to recognize whether this intermediate is actually formed or not. So you can say that this species is highly unstable. And this is the reason even we are seeing here that there are 2 steps are going on, though we say it is a single step reaction, because this species is highly unstable. If you want to recognize that what is the stability, how much time it will stabilize, so the time in which the electron from hydroxyl is reaching to the carbon, or the electron from carbon is moving towards the chlorine or completely moves to the chlorine, that time period is the time for the stability of the species. The electron runs with almost equal to the speed of light. And what will be the distance? Maximum 1 angstrom or even lesser than that. So this much small distance is traveled with the speed of light, almost speed of light, then what will be the time taken? That will be 10 to the power minus 14, 15, 16, 17 something. And that time is very small time. That means the system is highly unstable, and this is the reason we does not recognize it, and we say that it is a single step process. The reaction is called a single step process. But when you see this step, this will be considered as a slow. And how many molecules are participating in it? This one and this one. There are 2 molecules. That means 2 molecules are determining the rate of reaction in the case of the SN2 reaction, and this is the reason it is called bimolecular. During the process of reaction, what happens? The chlorine, you can see in this case it is on the right hand side, and in the product it is moving towards the left hand side. That means you can see the compound was somewhat here, recognized in the term of the thumb, and here it turns in the form of this one. That means inversion. So this reaction leads to the inversion in configuration. Then this is the sum of the property in the case of SN2 reaction mechanism. So in the case of SN2 reaction mechanism, the process runs in a single step. The process is a bimolecular process, and the process leads to the inverted product or the inversion product. Now we are going to see the rate of reaction. How the rate of reaction is determined, what is the rate of reaction in the case of the SN2 reaction. So in the case of the SN2 reaction, when you will see the SN2 reaction, the rate will be based on the stability of the intermediate. When the intermediate will be more stable, the reaction will be faster. But when you will see the stability of the intermediate, we have already discussed that this intermediate is this much unstable that we are not capable to recognize that whether the intermediate is formed or not. And if that such condition is there, then how we will find the rate of reaction on the basis of the stability of the intermediate? That means we are not capable to discuss the rate of reaction on the basis of the stability of intermediate. And if we are not capable to find the rate of reaction on the basis of the stability of intermediate, then how we will find the rate of reaction? Which one will go faster or which one will go slower? Surely there will be some other way. Now we will discuss on the basis of chances of approach. What is the chance of the approach for approaching on the nucleophilic center. If the chance will be greater, the rate of reaction will be greater. If the chance will be lesser, the rate of reaction will be lesser. And what will be the basis for this approach? The basis will be the steric hindrance. In the case of the compound, in the case of the species where the steric hindrance will be greater, the chances of approach will be lesser, and if the chances of approach will be lesser, the rate of reaction will also be lesser. So we are going to discuss the rate of reaction in the case of the SN2 reaction mechanism. So here we are going to see the rate of reaction in the case of the SN2 reaction mechanism. We are seeing some of the compound here, primary, secondary, tertiary, as well as the methyl system, and we are trying to find the chances of approach of the hydroxyl. When you will see the first one, surely the size of chlorine atom will be greater. But when you will discuss about the size of hydrogen atom, that will be the smallest in the periodic table. We say that the helium is smaller than the hydrogen, but when you will see any of the element which is reactive, then hydrogen is the smallest atom which can undergo the chemical reaction. So this is the smallest atom. That means the system is capable to generate the least steric hindrance. So in this case, the approach can take place from here, here, or even from the front one. We are not going to discuss about the front one because there is a inter-electronic repulsion is also working due to the identical charges on the case of the hydroxyl and the partial negative charge in the case of the chlorine. So from the back, there is a greater chance of the approach because hydrogen is very small and that have a very low steric hindrance. But when you will see the primary system, chlorine is here. Chlorine is available in all the four compounds, so we are not going to discuss about the chlorine because that is considered as a common factor. But when you see the other species, the hydrogen and one respectively bulkier methyl group, the alkyl group. And now what? The approach can take place, but when the approach is taking place from these of the positions, it is not possible because the size of methyl group is higher, the bulkier than the hydrogen. And this is the reason why the primary system have greater steric hindrance than the methyl one. Now we are seeing the secondary. This is the secondary compound having chlorine, a bulkier atom, having methyl, even bulkier, this one, and a small hydrogen. You can see the chances of approach becomes lesser because the steric hindrance is much more than the methyl system and even more than the primary system. So in the case of secondary, the steric hindrance is even greater. And what's about the tertiary? This is the chlorine, methyl, and the methyl, and another methyl. It looks like the system can't approach. Even it is a 2D, we are representing it in the form of the 2D, and the real molecule is in the form of the 3D. So surely there is a chance of approach. But when you will see the condition of the tertiary, the chances of approach in the case of tertiary is much lesser than in the case of the methyl, primary, and secondary. So surely you can say that the rate of reaction in the case of methyl is maximum, then it is primary, then secondary, and then it's tertiary. And all of these of the things are discussed on the basis of the steric hindrance because in the case of the methyl the steric hindrance is least, and in the case of tertiary system the steric hindrance is maximum. So this is the rate of reaction. But what's about the aryl system? What's about the aryl halide? Whether that will go faster SN reaction or the slower SN2 reaction? Here we are trying to discuss about the rate of reaction in the case of the haloarene, especially for the SN2 reaction mechanism. We are finding that what is the steric hindrance in the case of the SN2 reaction for haloarenes. When you will see the condition of the benzene, I have drawn the chlorocyclohexane. In the case of benzene, the unhybrid orbitals will be somewhere here. You have seen in class 11. And where are the electrons? Electrons are resonating above and below the ring. If the delocalization of electron is taking place on these of the position, what's about the charge on the ring? The electrons are surely negatively charged, so the charge on the ring will be also negative. So when this hydroxyl group or when the nucleophile will approach on the system, whether there is any chance for the approach on the carbon, that is the alpha carbon? Surely not. The benzene ring have a greater size, so that is generating the steric hindrance. But more important, the electrons, that is the electron clouds, are providing the heavy inter-electronic resistance. And due to that heavy inter-electronic resistance, it is very difficult to approach on the carbon for the nucleophilic substitution reaction. So we can say that the haloarenes are not a proper substance for the nucleophilic substitution reaction, especially in the case of the SN2 reaction, because the benzene is generating the steric hindrance as well as the inter-electronic hindrance. So the haloarenes have the least rate of reaction in the case of the SN2 reaction. So you can say the aryls are the slowest substances for the SN2 reaction. So this is the rate in the case of SN2 reaction. The fastest is the methyl, then primary, then secondary, then tertiary, then aryl. For the SN2 reaction, in the term of the steric hindrance, we have discussed on the basis of the steric hindrance. So this was the SN2 reaction. In the next video, we will see about the SN1 reaction mechanism for the same reaction. Till then, bye. Have a nice day.